Hello, welcome back. In the next two videos, I will talk about in-order successor in BST, or binary search tree. This question is from LeetCode, which is equivalent to LeetCode 285. That LeetCode question is a LeetCode premium question, but you can go to LeetCode and do this for free. I'm not associated with LeetCode, and this is not an endorsement, but it is another resource that one can try some of those LeetCode premium questions. We are given a binary search tree, and we're given a node in that tree. Our job is to find the in-order successor of that node. First, let's talk about BSTs. So this is a simple BST. You have the root nodes on top, and you have a left child and a right child. The left child has a smaller value than the root node, and the right child has a bigger value. So what is an in-order successor? If we are looking for the in-order successor of 1, that will be 2. If we are looking for the in-order successor of 2, that will be 3 in this tree. And if we are looking for the in-order successor of 3, there is none in this tree. Look at this tree. If we are looking for the in-order successor of 4, that is 5, which is the root of this tree. Essentially, we are looking for the node which has the next larger value. A naive solution for this problem would be to do an in-order traversal. As the name suggested, in-order traversal will touch nodes in an increasing order from the nodes with the lowest value to the nodes with the highest value. All we have to do is to traverse, and then once we hit the nodes that we're looking for, the next one is the one that we wanted to return. This would have the runtime complexity of O of n. The question here is that, can we do better? Well, it depends. There is a better solution, but whether we can do better, it really depends. I will explain later. But first, let's talk about this better solution. This is the function definition of the function that we have to write. We are given a root node of the tree and the tree node P. And what we have to find is the node that has the next higher value than the node P. Since we are given the root nodes, we know that we have to walk through the tree starting from the root. Now the decision to make there is that which branch of the trees do we have to go down? Now there are really 3 scenarios. The first scenario is that the value of P is equal to the root value. Second scenario is that value of P is greater than the root value. And the first scenario is the value of P is less than the root value. So first scenario, the value of P is the same as value of root. Where is the in-order successor of P? Well, it must be on the right subtree. So in this tree, this will be 6. Now there could be other nodes on the right subtree. Consider this tree is still 6, but notice where the 6th node is here. We can say that for scenario 1, the in-order successor must be on the right subtree, and what we are looking for is the minimum value on the right subtree. Another way of looking at this is that basically we are looking for the in-order successor starting from the right child of the root node. So we can do this. We are using the same function, and this we should return the in-order successor for the node P. So let's build up the pseudocode for the function. For scenario 1, if the value of P is same as the value for root, we just call the same function, but using the right child of root, and we're looking for the in-order successor of P. In the second scenario, the value of P is larger than the value of root. Where's the in-order successor here? In this scenario, both P and the in-order successor of P must be also in the right subtree, not including the root. We can just discard this entire portion of the tree. Again, we can call the same function, find the in-order successor starting with the right child of the root. Now we can add scenario 2 to the pseudocode. For scenario 3, the value of P is less than the value of root. So where is the in-order successor here? Well, it should be in this part of the tree, including the root. For example, if you're looking for the in-order successor of 3, then it's 4. If we're looking for the Inorder Successor 4, then it's the root itself. Hence, we can discard this part of the tree and focus on the left-hand side of the tree and the root node. On the left-hand side of the tree, we can break this into two parts. There is the left subtree and there's the root node. Now, one can imagine we can use the same Inorder Successor function and we can search the successor in the left subtree. And if we don't find the Inorder Successor there, we know the Inorder Successor must be the root node. Now we add scenario 3 to the pseudocode for the function. Now you can see that scenario 1 and scenario 2 are the same. We can just combine these two. And here, because we are returning, we can take out the else here. So now we can use this and convert to real code in the language of your choice and test this. This Java implementation is available in the GitHub links below. Everything here is very similar to the pseudocode I showed earlier. We start with the base case. This is very important. If root equals null, then return null. I always include this line for all the recursive function I write for trees. And this line here just covers scenario 1 and scenario 2. And these two lines covers scenario 3. Before we test this, let's talk about the runtime. The runtime should be big O of height of the tree. Depends on what kind of trees we are given. If it's an unbalanced tree, for example, we can have a very long one-sided subtree, then the runtime is big O of n. That's why when I said earlier, whether we can have an improvement compared to the Inorder traversal solution, it really depends on whether the tree is balanced. Now, if the tree is balanced, the runtime will be big O of log n. Now let's test if this works. And looks good. Next time, we'll do another question on Inorder Successor of a binary search tree. If you want to support this channel, please like, subscribe, leave a comment. I will see you next time.